Hello class, today we're on 4.6, inflection points in concavity. So, an interval of a function is considered concave up when the function is curving up. An interval of a function is considered concave down when the function is curving down. An inflection point is the point where the curvature changes direction. So they basically separate concavities. So we'll have sections where it's concave up, sections where it's concave down, and in the middle, that point where it switches concavity is going to be what we call an inflection point. So here I have graphed a function, and the orange dotted lines here are separating where it's concave up from where it's concave down. And notice that I have inflection points right here at those separation marks. So let's take a look at this first section on the left. Notice how it's concave down. It's like an upside down cup, right, or something like that. And then this next portion is concave up. My professors used to say it's concave up like a cup, right? So it's going up, and this next part is concave down. It's bending downward, right? It's like an upside down cup, if you will. And then this last part is concave up. So we're talking about these intervals of concavity. So let's talk about that. Well, first, let's identify these inflection points right here. So our inflection points are x equals, let's see, this is negative. If this is negative 2, this would be negative 1. So our inflection points exist at negative 1, 0, and positive 1. So negative 1, 0, positive 1. And then now we want to know where is it concave up? Well, it's concave up here, or this section, and it's concave up this section. So remember how we write intervals. We're going to write them in as parentheses, or in parentheses, sorry. So our first interval of concave up is from negative 1 to 0. So we'd write from negative 1 to 0. And then our next portion of the concave up is from 1 to positive infinity, because it remains concave up as it reaches towards infinity. So this would be from positive 1 to infinity. And that should be an infinity symbol. It's just not very good. Sorry about that. There we go. Okay, so now where is it concave down? Well, it's concave down this left section and this middle right section. So it's concave down from negative infinity until we get to negative 1. And it's also concave down between 0 and positive 1. So that's how we'll be writing them. Okay. So that's concavity and inflection points. Now our question is, how do we find inflection points? And how do we find inflection points and where a function is concave up or concave down? Well, to do that, we use what we call the second derivative test. And as you could imagine, we use the second derivative for that. So an inflection point exists where the second derivative equals 0. And more specifically, where if it crosses the x-axis. Sometimes we'll get like a bounce on the x-axis, but that doesn't change concavity, as you'll see in one of these examples. So it needs to cross the x-axis. Also, f of x is concave up when f double prime of x, so when the second derivative, is positive, or above the x-axis. F of x is concave down when f double prime of x, or the second derivative, is negative, or below the x-axis. So, today we're going to be using Desmos to help us figure this out. We are going to take the derivative algebraically, or the second derivative algebraically, and then we're going to plug that into Desmos to check where our inflection points are, and where it's concave up and where it's concave down. So, let's give some examples. Here we have their function f of x. So let's go ahead and first start off by taking or finding the second derivative. So, if I have f of x is equal to x to the fourth minus 4x squared minus x plus 1, the derivative would just be, let's see, f prime of x is equal to 4x cubed minus 8x minus 1. And then the second derivative will just be taking the derivative again. So it's going to be 12x squared minus 8. So let's graph our second derivative and figure out where our inflection points are and where it's concave down and where it's concave up. So here is the graph of the second derivative. This is the graph of 12x squared minus 8. And here we see that it crosses, well, first it starts off in positive land, so that means our f of x function, our original function, is concave up in this section. And then there's an inflection point right here, and then it becomes concave down for a little bit. And then there's another inflection point, and it becomes concave up again. Of course, I'm not talking about this derivative. I'm not talking about the second derivative function. I'm talking about the original function. This is just what the second derivative is telling me about the original function. So we have an inflection point at negative 0.816 and another inflection point at positive 0.816. So our inflection points here are at x equals negative 0.816 and at positive 0.816. So let's see. It's going to be concave up. Well, let's talk about it. There's going to be two sections of where it's concave up. It's going to be this section on the left and this section on the right. So where is that in terms of x? Well, it's concave up from negative infinity to this point at negative 0.816, and then it's concave up again from 0.816 to positive infinity. And then where is it concave down? Well, it's concave down in the middle there at, let's see, negative 0.816 to positive 0.816. All right, and just before this, let's go ahead and graph the original function. And here I have the original function in orange, so we can see it first. Oh, let me. I guess I'll turn off the second derivative. So it exists concave up, right, until we get to like this point right around here, and that should be at the 0.816, and then it becomes concave down for a little bit until we get to right here, and that's about 0.816, and then it becomes concave up again. So you can see them both overlaid next to each other. So that's some pretty cool stuff right there. The second derivative tells us a lot about a function, just like how the first derivative tells us a lot about the function, right? First derivative tells us where it's increasing, where it's decreasing, and we have those critical points where the first derivative equals 0. Second derivative tells us where the critical points are. Inflection points. Second derivative tells us where the inflection points are. Okay, let's go on to the next example. So again, first thing we're going to do is find the second derivative. So if we have f of x is equal to x cubed minus 4x squared plus x minus 1, f prime of x is going to be 3x squared minus 8x plus 1. And the second derivative, f double prime of x, is going to be 6x minus 8. Awesome. So now let's graph our second derivative of this example. And we get this linear function as we kind of expected, right? 8x, or what was it? It was 6x minus 8. So this is what it's telling me. It's telling me that our function exists as concave down until we get to this point right here at 1.333, and then it exists as concave up for the rest of it. So let's see. We have an inflection point right at 1.333. Let's just verify this. Let's see what our original function looks like. Okay, so yeah, perfect. So right at this point, at x equals 1.333, it changes concavity, right? To the left of my pen, it's concave down, and to the right of my pen, it's concave up. So let's see. We have an inflection point at x equals 1.333, and it's concave down, looking at that second derivative, the function in black. It's concave up from 1.333 to positive infinity, and it's concave down from negative infinity until it gets to that point at 1.333. Awesome. All right, so we got two more examples here. I'll go ahead and turn these off. Okay. So now we have our new f of x, negative x squared minus 3x plus 4. So let's go ahead and find the second derivative. So the first derivative is going to be negative 2x minus 3, and the second derivative is going to be negative 2. So let's go ahead and graph these, or graph this this second derivative. Where'd it go? We're on the third example. Okay. So here we have the graph of the second derivative. Notice it's just a flat line. It doesn't even it has a slope of 0. So this is what it's telling me. This is telling me that this function doesn't have an inflection point. It doesn't cross the x-axis, and it's concave down the whole time. And that should make sense, just even looking at our original function. Right? This is an upside-down parabola, or it's a parabola that's opening down, meaning it's concave down the whole time. So let's just double check. And there we have it. It's concave down the whole time, and there aren't any inflection points. So really cool stuff. Really cool stuff. Okay, now let's go to our last example here. F of x equals x to the fourth times e to the x. So again, let's go ahead and find the second derivative. So this is going to be an example where we're going to have to use the product rule, our good old friend, the product rule, because we have an x and we have multiplied to something with an x in it. So let's see, the product rule, if we recall, is the first one times the derivative of the second one, and let me just put that little thing there, or this multiplication point, so we can see it's x to the fourth and e to the x. Our derivative of e to the x is just e to the x, plus the derivative of the first one, 4x cubed, times just the second one. Awesome. Okay, so now let's find the second derivative. And here we're going to have to use the the product rule twice, because we have this section that has two things that are with x that are multiplied, and we have this one on the right where we have 4x cubed, and we have e to the x. So, doing this one first, again it's the first one times the derivative of the second one, plus the second one, or sorry, the derivative of the first one, times the second one. So what I've done so far is just this section, right? I still need to do this section. Plus, let's see, the first one, 4x cubed times the derivative of the second one, e to the x, plus the derivative of the first one, that's going to be 12x squared, times just the second one, e to the x. Awesome. Let's clean this up a little. Notice that we have like terms right here, right? So we can add them. I mean, you don't have to, but I kind of like doing it. Okay. Boy, that's an ugly derivative, right? Okay, so let's go ahead and graph that second derivative. And looks a little funky, right? But it looks like we have an inflection point here at -2. And then here, notice, remember what I said earlier. This, although it touches the x-axis, it doesn't cross the x-axis, which means that the concavity doesn't change, does it? So it's concave down, then it becomes concave up, and then it remains concave up. It doesn't change concavities right there. So in order for it to be an inflection point where it changes concavity, it needs to actually cross the x-axis. So our inflection point, we didn't even do the inflection point stuff. We'll come back to this one. So the inflection point of this one, this just has 1. It's at x equals -2. And let's see, it's concave up from, from -2 to infinity. And it's concave down from -infinity until we get to 2. Oh, I goofed. There are 2 inflection points here. There's also an inflection point at -6. I should have looked at that. So there's an inflection point at -6, and then it's concave. Ooh, okay, so that's going to change this. So it's concave up from -infinity. I goofed here. All right. It's concave up from -infinity to -6, and then also from -2 to infinity, right? And then it's concave down in this little section in the middle here, from -6 to -2. All right. I should have looked at that. And let's check to see. So in the orange I have our f of x, our original function. And as you can see, let's see here. It's concave up slightly, and then it goes slightly concave down for a little bit until we reach this point right here at -2, and then it's concave up for the rest of it. Very good. Okay. So let's go back to our last example. Oh, it's because there were no inflection points. That's right. That's probably why I got confused here. So, or not confused, but forgetful. So the inflection point here, there's none. And it's concave up, never. But it's concave down from -infinity to positive infinity. Or I guess here we could probably say in a non-applicable or something like that. But yeah, so that's a concavity and inflection point. So that's all I have for y'all today. Let me know if you have questions, and have a good day.